write a couple generic equilibrium statements. So let's take a look at an equilibrium statement. Let's write an equilibrium statement for the following. We have two reactions shown. Let's write the equilibrium statement for each. You can write this as Kc or Kp, I don't know. So it's a good time to hit pause and test your knowledge. Of course, I'm not going to make the "did you hit pause" joke, but it's tempting. So for these two equilibrium statements, let's take a look at the first one. We can write the balanced equation, H2CO3, H plus 2 plus CO3 minus 2. These are all aqueous, so we can write, traditionally we could write this as a concentration-based equilibrium constant. And so we can, the general form is always products over reactants. So this would be H plus concentration squared times carbonate concentration minus 2, all divided by the carbonic acid concentration. This would be the form of the equilibrium expression. So let's take a look at a more complex example. 2 NO2 gas plus 7H2 is in equilibrium with 2 NH3 gas plus 4 H2O gas. Again, products over reactants. This would be NH3 times H2O divided by H2 NO2 with H2 being raised to the 7th power, NO2 being raised to the 2nd power, H2 being raised to the 7th power, and H3 being squared, and H4O. That would all equal Kc. If we knew those concentrations, we could plug them in and go. This, being able to generate an equilibrium constant from an equilibrium expression, is key in this particular part of the class. Every single time you write it, every time you see the word equilibrium in a problem, I need to see both of these. You need to see both of these. It will save yourself much gray hair. Sometimes, though, you will have a solid or a liquid. These are what we call heterogeneous equilibrium expressions. Rather than being all the same phase, we'll have materials that have different phases. How do we deal with them? And it boils down to this idea of what we're actually measuring with the equilibrium constant. What we find is that solids and liquids have no appreciable change during a chemical reaction. Their concentrations do not change. like I said, water is 55 molar. You know, you take away some water, it's still 55 molar. And so the concentration doesn't change. And because it doesn't change, it has a distinct impact on the equilibrium. They are eliminated from the equilibrium because they are constants. They actually get folded into the equilibrium constant. And so the correct equilibrium expression for solid, things controlling solids and liquids, are neglected from the equilibrium constant. So this particular one, KEQ, would be equal to magnesium carbonate is a solid, magnesium oxide is a gas, solid, carbonate is a gas. Products over reaction, the equilibrium constant would just look like this. These are not considered in the equilibrium expression because they are solids and they don't contribute, they don't significantly change during the course of the reaction. Similarly, with a liquid, a pure liquid, not a solution, a pure liquid, the same behavior applies. So reactions that are done in water, often again the water is not included in the equilibrium expression because it has a in the liquid state, water has a constant concentration. So we talked about the form of the equilibrium constant. So Kp would represent the partial pressure of something like NO2 going to N2O4, partial pressure of NO2 squared divided by partial pressure of N2O4. Though this would be the form of the equilibrium constant. So just as a tip, you should have a balanced equation. And if you see the word equilibrium, you should have an equilibrium constant form written out. You want to write out that equilibrium equation because that equilibrium constant is going to be central to everything you do. So let's take a look at a real world example. This is how to calculate an equilibrium constant. How do we do that? Well, we've already have a clue. The equilibrium constant has to be calculated from equilibrium concentrations. So the easiest way to do that is to measure the equilibrium concentrations of all your species involved. Of course, what we need to do is we have to measure the species, both the reactants and the products. But we don't necessarily have to measure them all directly. We can also measure them indirectly, thanks to the wonderful world of stoichiometry. So, how do we go about doing this? Well, let's take a look at an example. So we have a reaction mixture. Put this in here. We're going to start with nothing but N2O4 to start. We find that the pressure is 0.640 atmospheres. Sorry, 0.670 atmospheres at the start. You let this stuff sit around for a while, and what you'll find is that over time, you'll eventually reach equilibrium, and you'll see 0.0547 atmospheres of NO2 and 0.643 atmospheres of N2O4 have developed in this reaction. And we can plug those values in, we just bring them down. So at equilibrium, we see 0.643 atmospheres of the N2O4 divided by 0.0547 atmospheres squared to give us the following value. Plug it into our calculator. 0.643 divided by 0.0547 squared gives us a value of 214. And the units, well, what are the units for this? Well, judging by our description, this would be inverse atmospheres. But equilibrium constants are traditionally reported unitless. Because in reality, we're actually not measuring pressure or concentration. We're measuring something called activity. Activity is related to, is proportional to concentration when concentration is low. And so for the most things that we'll be doing, activity will be equivalent to concentration. So we traditionally will write it as a unitless quantity. This gives us our equilibrium constant. So notice we started with nothing but N2O4, and then the reaction progressed backwards to produce NO2. And then it reached equilibrium, eventually stabilizing. So this would represent the equilibrium constant for that system. So let's take a look at the same equilibrium using a different set of starting conditions. So instead of starting with all NO2, N2O4, in the last example we started with nothing but N2O4. And we saw that the reaction ran itself backwards to produce NO2. And that was just given in the problem. Again, this is always the starting material, and this is always the product. If we reverse the reaction, then that's something different. Then now the N2O4 would be the starting material, but we're not considering reversing the reaction. We're just looking at it as a matter of perspective. Again, associated with this is the following equilibrium constant, Kp, K equilibrium. Kp is equal to the partial pressure of N2O4 divided by the partial pressure of NO2 squared. All right. So if we take a look off to the left, what we see is some conditions. We see that if we start instead with N2O4, we start with 0.200 atms of NO2, and then we let the reaction progress. What we see is at the end, we say that there's 0.0204 atmospheres of NO2, and in that process, there are 0.0898 atmospheres of N2O4 formed. So again, this is the final conditions. This is the equilibrium. And that's what we care about. We care about the equilibrium concentrations, equilibrium partial pressures. Once we have those, we can plug in those values. Kp, we have our 0.0898 atmospheres of our N2O4 divided by our atmospheres of NO2 squared. And then we can plug that into our handy-dandy calculator. So looking at what we see is that we get 215. And if we take a look at our previous example, we see that these two numbers are effectively the same. These two numbers are effectively the same. And so, even though we had two different starting conditions, all NO2 versus all N2O4, they both attained an equilibrium state that gives us exactly the same equilibrium constant. Kp is equal to 215 versus Kp is equal to 214, which are, in this case, within rounding errors. These are the same. Additionally, notice that the concentrations at equilibrium aren't necessarily the same. For the two reactions. So they're not the same for the two reactions, but yet the ratio between them is the same. So you go back and take a look and you'll see that we had very different equilibrium concentrations. Net result, though, is that the ratio is the same. And so this is what we see. Reactions will try to get to equilibrium, and they'll progress to equilibrium. And once they're there, then they produce, they stabilize to a ratio that is effectively the same for those components. So let's think about equilibrium constants for a second. So let's think about equilibrium constants, KEQ. An equilibrium constant, again, is you can think of it as approximately equal to the ratio of the products over the reactants. It's not that simple. If we look at our previous examples, our equilibrium constant, Kp, was 215, and what we saw in both of those cases was that there was more N2O4 and less NO2 at equilibrium. So we can do a quick analysis of equilibrium constants and make some simple arguments. If the equilibrium constant is really large, say we'll say greater than about 1,000, we can say that does it favor the products more or the reactants more? By favor, I mean if we have reactants in equilibrium with products, since the equilibrium constant is effectively a ratio between these two, one of these is going to dominate at equilibrium. Is it going to be the products or the reactants? So if it's a very large equilibrium constant, we could say that it's the products that are going to dominate. The ratio of the products to the reactants is equal to 1,000, then we can assume that, well, if it's greater than 1,000, then that is where the bulk of there's 1,000 times as much product as reactants is another way of looking at it. So you can do this quick estimate by looking at the equilibrium constant. So very large equilibrium constants lean heavily towards the products. We can think of the reaction moving preferentially towards the products, effectively eliminating any of the reactants, or the amount of reactants being present is very small. Conversely, if the equilibrium constant is small, we'll say significantly less than 0.001, we could say that that the reaction would favor the reactants. Now, when it's in between these ranges, you could say that there'd be significant amounts of each present. Now, this is an approximate. You can't just use this to just make the assumption. This is an approximation. because what happens is with squared terms, particularly when you have low concentrations, these numbers can become a little bit tricky. But for the most part, very high concentration, very low concentrations, you can use your chemical intuition to tell you that the reaction is all products or all reactants, or mostly products or mostly reactants, which turns out to be very helpful for us when making assumptions. Now we have a bit of information that relates to the relative ratios of the products.